welcome to the 66th Theoretical Physics-Colloquium by Professor Scott Pratt, who's a professor of National Superconducting Cyclotron Lab at Michigan State University. He received his PhD from the University of Minnesota in 1985. He spent several years at several places for postdoctoral training, and then he joined the faculty of University of Michigan State University in '92, and he remains there since. Over the years, he received some awards and honors. One of them I should probably mention, a teaching award at Michigan State University, several teaching awards perhaps, and he was working as divisional associate editor for Physical Review Letters. He actually served 2 terms in early 2000s. His research interests include theory and modeling of heavy ion collisions, properties of quark-gluon plasma, hydrodynamic and kinetic theory description of heavy ion collisions, transport properties of quark-gluon plasma, interferometry, and charge balance correlations in heavy ion collisions, and many other things. And today he will be talking about extracting the diffusivity and charge susceptibilities of QGP from experiment. And with that, I'll give the microphone to Scott.
Okay. Thank you, Igor. Okay. So the diffusivity and charge susceptibility, these are 2 very fundamental properties of the quark-gluon. So these are 2 fundamental properties, and you can list your own list of fundamental properties, but principal among them are going to be, let's say, look at number 2 on that list is the chemistry, which is related to the charge fluctuations. And when I say it's fundamental, if somebody asked you to describe the quark-gluon plasma, they would say, oh, it has a bunch of free quarks. And if you knew the temperature, you would know how many quasi-particle quarks of each of light flavors was running around. And that reflects itself mainly because the net amount of strangeness is 0, let's say, but the fluctuation tells you about the actual number of quarks. And also another item on that list is the diffusivity, which is a fundamental transport coefficient, similar in its importance as the viscosities. So these 2 properties, if you want to learn about them experimentally, the best way we have of looking at those is, as I'll make a case for during this talk, is through these charge balance correlations. And by charge balance, it's basically saying if you see a positive, you know there's an extra negative somewhere. And so you do a like sign subtraction and find how close in rapidity, relative angle, relative momentum, the balancing charge is to a given charge. And you can index that based on whether the charges are in kaons or pions or protons, et cetera. And so those are the observables, and that class of observables has the tightest connection to these two properties. Charge balance functions are also important as background to other processes, but that's not the subject so much of this talk. So I'll start off with the theory stuff. It's supposed to be a theory colloquium, so I'll begin by just giving you some kind of way to think the sort of paradigms of ways to understand and think about charge correlations. So typical way you would describe a correlation in a book is you would just take by delta rho, you would mean the charge density minus the average charge density. And you would see how it's correlated based as a function of say the relative position. And in this case, I have C sub AB, and the AB are indices referring to flavor. And I'm just talking about light flavors, so up-down strange. So the correlation is also a 3x3 matrix and a function of R1 and R2, or if in a uniform system, just a function of delta R. And if the system is equilibrated, then you would see that it would have to integrate to the charge fluctuation, which is the susceptibility. So the strength of the correlation is the susceptibility. So when they measure the susceptibility on lattice, that is the strength of the correlation function. Now I say it's a delta function, but I'm using delta function loosely, meaning some function that integrates to 1 with some small scale. So as long as the correlations are not long scale, well, let's say we're away from phase separation of the critical point. So let's take those out of the discussion for a while. Then pretty much all the other correlations we talk about are short range. In that case, I'm going to say that short range spread is encapsulated by delta. So it doesn't have to be a perfect delta function, but it's just some kind of short range function that integrates to unity. Now, I said earlier that the susceptibility is the best way of looking at it at the observable, rigorous observable for understanding the chemistry. And in a quark gas, or in any gas, any quasi-particle is uncorrelated with any other quasi-particle. So the only correlation when I get from delta rho, or delta Q, is between the charges on the same quasi-particle. And so in a quark gas, the susceptibility would be just proportional to the density of each species, and it would be diagonal, okay, because I'm in the UDS basis, not the electric charge baryon number strangeness basis, but the UDS basis. So if I'm in a quark basis, it should be diagonal and then proportional to the densities. And so therefore, if you see from lattice actually above 200 MeV temperature, you see that the susceptibilities are remarkably close to what you expect for a free quark gas. In a hadron gas, you can have multiple charges on a hadron. And so then what you do is, again, you sum over each species. N sub h is the density of each species. And then it's the charge, product of the charges of type A and type B for that species. So again, the hadron gas has a very specific kind of susceptibility. Now, if we look at these susceptibilities, now I'm scaling these by the entropy density. And so on the right of the dashed lines there, I have lattice results. And to the left, I just have what you would expect from a hadron gas. And there's a little window around the dashed line that is a sort of interpolation. But you can see they match up pretty well at lower temperatures. And at very high temperatures, you see that this ratio goes to what you would expect from a parton gas. At a large temperature, because the up and down are a little lighter, you expect this red line to be a little higher than the green line because there's a few more up quarks and down quarks, but that becomes irrelevant as the temperature rises, large compared to the slight mass difference between strange and up and down quarks. And in a hadron gas, notice that you get these off-diagonal elements, not because you have some hadrons. For example, a pion has both up and an anti-down quark. So if you see an up, there is you may expect that there's a good chance you'll also see an anti-down. So that's a negative contribution to the susceptibility because it's an anti-down quark. So as you come into the hadron region, the susceptibilities get these nice conditions. And notice that chi-SS goes to 0, and that's just because that kaons are heavy, and if you when you cool down, they disappear. They don't carry a decent fraction of the entropy.
Quick question. Quick question here. Not charm quarks.
No charm quarks. I'm just doing up-down strange, 3 by 3. So I'm just going to leave that for an entirely different community. Not okay. And you can also, plot just for grins. You can plot the susceptibilities in the other basis, the charge, electric charge, and baryon number basis, and you see kind of the same thing. What you'll notice is because baryons are heavy, the baryon susceptibility also wants to fall, because baryons start carrying very little of the entropy. If you were down at 50 MeV temperature, there'd be basically all you have is pions at that point. Now, so if you want to look at that a little bit more visually, if you had a pion, this would be, let's imagine we have a pion gas. So we just have these, a pi 0 won't contribute to anything because it has an up and an anti-up, or a down and an anti-down. but you'll just get these contributions from pi pluses and pi minuses to the charge susceptibilities. And you'll, and if I look at the up part, there will be a short range part. Now in an equilibrated system, but if I'm in a dynamic system, so now imagine you're in a heavy ion collision basically, and in that case, I know if I have a pi plus, there's another pi minus somewhere, okay? And because these correlations have to integrate to zero. So this is the difference between a charge correlation in an equilibrated system and in a dynamic system. In our dynamic heavy ion system, charge doesn't fluctuate. The net strangeness starts out at zero, it's zero. Same with upness and downness. And what that means is that the correlation functions have to integrate to zero. Okay. And now, if you had a box, let's say we had a box, a static box full of gluons, and then it thermalized and made bunches of quarks, what you would have, let's say it's a very, very big box, then this balancing correlation, the part that's different than the thermal distribution, would be spreading out over large time. And over, if you waited a million years and it was a very, very, very big box, you're just going to be left with the equilibrated part at the end of the day, and the other part will be still equal strength, but spread over infinity. And if I look at the up-down part of the correlation, so jump over here to the right figure, it's the same thing, except that is negative, because now when I see that up, there's an anti-down, as opposed to seeing it up, well, I know I also have the up that I just saw. So it's actually equal and opposite strength, but is negative, and the balancing correlation has exactly the opposite size and shape. So when I describe the correlation, there are two pieces I'm going to talk about, especially for the model we're going to talk about. We're going to assume that the local part stays equilibrated. And when I say the local part is equilibrated in the correlation, that is akin to saying I have basically local chemical equilibrium. It's basically the same statement. So if you're assuming you have local chemical equilibrium, then what you're basically saying is that the correlation function has this, so chi AB is the equilibrated value, which is a function of the local temperature, plus the balancing correlation. And it's this balancing correlation that's going to give us the insight into everything we want to do. So the balancing correlation is the gold here. At the end of the day, you measure the particles, how many pions or rho pluses or omegas, whatever you want to say is your chemistry at breakup. You measure that. So in a sense, that gives you this first piece. This other piece is where the balancing charge is. That's the correlation that comes from the balancing charge. If you saw positive, somewhere else there's an extra negative. And so in a sense, that's what this is going to represent. Now, if I want to think about how these correlations evolve over time, then if you, and then let me just write these equations for a system that's uniform in space, so it's not, equations aren't quite so ugly. So I have this balancing correlation, and it will diffuse over time. Imagine if you have a positive and a negative, they will diffuse away from one another over time. So this first left-hand side just looks like the diffusion equation of two charges diffusing away from one another, all the way to the equal sign. Now on the right-hand side of the equal sign, that's a source function. So that's the part that's contributing, it's either increasing, or it can have a negative contribution too, sourcing this C prime with a positive or negative piece at R1 equal to R2. And because this integrates to unity, you can see that what happens, the source function has to be proportional to how chi is changing. Chi times, say, the volume of a fluid element. The amount that changes means the source function has to change if the integral is going to remain zero. And so the time evolution of chi is what matters. And if you'd like to, you can think of, if I have entropy conservation, then you can write it like this instead of including this del dot V piece here, which includes the fact that the volume element is increasing. You can just write it as time rate of change of chi over S. And so that's why chi over S is such a critical thing to understand, because now I can look over here at this left figure, and I can look at chi over S and understand how I'm sourcing the correlation. Okay, so let's say I start off, there's nothing there, then the heavy ions pass through each other, and the first 0.6 or whatever Fermi over C, you chemically equilibrate the system. What that means is that during that time, the source function had to integrate enough to jump you up to this height of this of the line here. Okay, so think of that as initial like pulse of a source. Then if it stays flat, then I don't contribute any more to that source function. The correlations, the C prime, the balancing correlation just diffuses and becomes broader and broader. But then as you come to hadronization and you get near temperatures of 160 or so, then the susceptibilities jump up a lot. And what's happening here is that you're making a lot more quarks, especially up and down quarks. Just think of a box full of quark gluon plasma that you then isentropically expand, and because of conservation of entropy, you're going to have about 80% as many hadrons as you had of partons. But each of these partons has multiple quarks. And whereas, for instance, the gluons didn't, and the partons that didn't have any quarks. And so what you end up, if you just do sort of a, crude estimate, you'd say, my God, I have to basically triple the number of up and down quarks, nearly triple it, when you hadronize an ideal quark gluon plasma. Number of strange quarks, because the kaons are heavy, doesn't change so much, by the way. And so what happens is the susceptibility is here, this rise corresponds to a source function to chi. So you'll be feeding C prime at R equals 0 at later times. So you can think of as, in some of our old papers where we weren't really doing these three-dimensional pictures, we called it a two-surge picture. The first surge is when you make the quark gluon plasma, you make a bunch of charge, and all those charges have balancing pieces. Then there's kind of a desert of particle production. And then when you hadronize, there's another surge. And that surge is mainly through the up and down. Now, if I go here on the right, and this is integrating over hydroevolution, so we can take a hydroevolution, and we know the temperature at every point in space-time, and therefore I know chi is every point in space-time, so I know the source function.
Scott,
and you can, yes.
We have a question.
Yes, I wanted to ask, you say the number of strange quarks is not going to change after hadronization, but that's the whole strangeness suppression story, where the number of strange quarks is supposed to change. How do you reconcile that?
I think you're, excuse me, sorry about that. Usually when you talk about strangeness suppression, you're talking about like canonical or or canonical enhancement. I'm not sure what kind of suppression you're talking about for strangeness.
Yeah, when I'm talking about suppression, I'm talking about from protons to heavy ions.
Well, to heavy ions, the strangeness increases, like k to pi, because there's a
yeah, so
canonical enhancement, which is, or actually it's more like
suppression or strangeness enhancement. So, in my understanding, when you
thermalize
you thermalize hadrons, you get different strangeness content.
That's more a question of whether or not you had time to thermalize and for a big heavy ion collision, the chemistry for strangeness, like k to pi or whatever you want to look at, it's pretty much equilibrated. It doesn't have, the canonical suppression becomes very unimportant in a central heavy ion collision. In a PP collision, it would be different. And in a PP collision, you probably wouldn't want to say that the correlation, when I said the correlation was chi AB times the delta function plus C prime, that local part, you wouldn't want to just assume that it's equilibrated. And you could pick a different function if you had some equations of motion for the local chemistry. But for here, for this, let's just think about heavy ion collisions.
Yeah, I thought not about canonical, but anyway, okay, let's postpone that.
Yeah,
it's going to be more.
Maybe I don't understand your question, but for let's stay in the context of heavy ion collisions, central collisions, where we are assuming the chemistry is, at least for the moment, will be equilibrated. And that can be loosened actually. And on the right side of this, the figure here, I'm just giving you an idea. This is integrated over X, Y, and Z, or X, Y, and X and Y in a Bjorken picture. And it gives you some idea of what the source functions look like. If I look at the SS strange piece, for instance, there's this big surge at the beginning, but then as things go through hadronization, they actually have some drop and you have some negative contribution. And the same, and whereas up stays all positive. And so up will have this contribution from late times, very significant contribution from late times, where SS will have a small contribution, which will actually be negative. Okay. So now when I have these correlations indexed by up, down, strange, and there can be even off diagonal elements, and I'm going to follow those when I talk about my calculation, or our calculation. We follow those through the hydrodynamic part of our description, but then typically you go through some hypersurface and you emerge on the other side of the hypersurface into some kind of microscopic hadron simulation world. And to do that, you need to translate the correlations with UDS into correlations indexed by hadron species. So instead of UDS, we want to use something that like pi k p lambda, lambda whatever. And so you can do that, but to do that, you just have to understand how, for instance, a differential amount of charge in this UDS basis, let's say a tiny bit of strangeness, how does that translate into a tiny, what's the ratio of translating that to a tiny amount of pions, kaons, lambdas, protons, etc., for any of the hundreds of hadron species that you would have. And you can work that out just thermodynamically, just assume you have a small amount of charge in a system and ask how much it changes each density. And it's a cool thing about that is it also depends on the susceptibility. So here it says that, let's say H is for K plus. So if I want to know how many extra kaons I get for delta QB, and this could be, say, an amount of upness, then I'm going to take the density of such hadron, of the hadrons of my K pluses, multiply it by this differential charge, and then multiply that by this matrix chi-AB, which is just the inverse susceptibility, and then also times the charge of type A sum over A. Okay. So it's a cool. You can work that out. It's kind of neat little exercise to do. But what that means is that I then know my correlations. If I know them in AB, I know what they should also be in indexed by hadron species. And what a balance function is going to be is it's going to actually refer to the final measurement. But it's very much, if you know the correlations in coordinate space, you can then translate those to correlations in momentum space once the particles are created. And the balance function is defined with this extra part of the denominator so that it reads like a conditional probability. So it reads like, if I saw a hadron of species H prime with momentum P2, what is the probability of seeing species of type H of the opposite charge? So H and H prime are both, it could be pi plus or pi minus, K plus, K minus, but of the opposite charge, and with momentum P1. And these momentums could be just relative momentum. It could be relative rapidity, relative azimuthal angle. And so then that's all it is. If I integrate over all species, if I say H and H prime refer to all charged particles, then it just means if I saw a charged particle at P2, what's the probability of finding one of the opposite charge, extra probability of finding one of the opposite charge at P1. So it's sort of a statistical like sign subtraction way of isolating the balancing charges. Now, you can take this factor here, think of this as a matrix which translates delta, the UDS basis to the hadron basis. And you can apply that to, like as a kernel think of it, you can apply that to these susceptibilities, and then you can think of where the source functions will be contributing to the various different kinds of balance functions. So let's say I do a pi balance function. That just means I only use charged pions when I create my balance function. Okay. And what you can see is that you get the susceptibility, this is chi over S. The contributions are going to come from very much from the late times where it jumps up like crazy and decays and stuff. If I do that for kaons, it goes up and then comes down. For protons, it also doesn't rise but comes down. So with protons, it's interesting because you might think physically that because protons have a lot of up, down, and strange quarks, and you know you may have a lot of up and down quarks in them, and you're making up and down quarks like crazy during hadronization, but they're very heavy. And so relatively little are in them. And so when you actually work it out, what it comes out to be is rather flat. And so if you're thinking about what's going to, how the proton-proton balance function is going to behave, it's going to have this big jump at early times and then be pretty flat and then have nothing. So the making balance function using just protons and antiprotons is a good way to see how the charge that was created very early separated. The same thing for kaons, whereas pions will be basically almost dominated by what happens by the production at hadronization. So if you see a pion, good chance you'll find another pi minus close by in rapidity and relative angle, because the source gives a strong contribution from this late stage hadronization, but not for the protons and the kaons. So what you expect, and this is very qualitative, but I think really crucial, is that if you measure the balance function for pions, it would actually be narrower than kaons or protons, and that is rather unintuitive. If the charge separation in coordinate space was the same for pions, kaons, if it really didn't depend on them, you would expect the protons to have a much narrower balance function because they have low thermal velocity. And you would think, well, if I have a p and a p bar separated by 1 Fermi, well, in rapidity, they're going to stay pretty close in rapidity because there's little thermal velocity. If I have a pi plus and pi minus, they're going to separated by 1 Fermi. Then their thermal velocity smears out the coordinate space correlation much more, and they'll be further separated in rapidity. But this tells you, this figure on the right tells you that we could expect to see exactly the opposite behavior. And seeing that exactly the opposite behavior would be a strong sign, that signal that the chemistry was evolving like you expect for an equilibrated system. And to put it another example, suppose you just had a gluon gas that hadronized after 5 Fermis over C. If that was true, then all these correlations would be the same width in coordinate space, and then translated into momentum space, this hierarchy would be the exact opposite. So this is a really nice way to get a handle on the chemistry. Of course, what's going to another thing that determines how the charges separate is the diffusivity. If the diffusivity was 0, then being created early or late wouldn't make any difference. So you're going to have to insert a diffusivity here, and these are just a couple of equations just to remind you that the diffusivity is a 3x3 matrix. In an ideal QGP, you expect it to be diagonal in the UDS basis. You don't expect strange quarks or to diffuse differently than up and down quarks. It's also related to the conductivity just by a factor of the susceptibility. And so the conductivity, the flavor conductivity and the diffusivity are basically the same, same quantities. There's a Kubo relation, and you can calculate it from lattice gauge theory. And that has been done, although people will say maybe they don't believe the error bars from the calculation. So now that I've hopefully given you sort of an idea about correlations and balance functions, I want to just review how we actually go about calculating the evolution of the correlations and get the charge balance function in a realistic model, with a usual what I would call the standard model of a heavy ion collision evolution with a hydro stage and a hadronic simulation at the end. And so main thing I want to point out is that we start off, we're doing the hydro stage is that we run a hydrodynamic code all the way through, and then we store the evolution. So it's a pretty big, nasty file. And then for each file, at each point in space-time, I know the temperature, I know chi. And so I know how chi changes with time. And so I take that time evolution of chi to generate the source function. Now, instead of actually calculating a six-dimensional source function at each point in time, we actually represent that Monte Carlo, represent the correlation function, or represent C prime with sample particles. So there's because diffusion is the same as a random walk, it becomes very efficient to just treat it, represent the correlation. Say I'm looking at the UD correlation function, and it's supposed to be negative because the source function went down. I can make a little up quark sampler and a down quark sampler, give a negative weight because it's supposed to be a D bar, give it a negative weight to that correlation, and then instead of solving some kind of horrible diffusion equation as for how they separate it with time, I can just Monte Carlo a random walk. And now because our little
how do you know chi from the temperature alone?
Oh, from I'll mention that in our case we're using the lattice results.
Oh, okay, that's fine.
Okay, and I'll mention that some of that in the future. So we represent the diffusive spread Monte Carlo in a Monte Carlo way by using the equivalence of a random walk and diffusion. The one difference that's really different between a random walk and a diffusion is that a diffusion equation actually has acausal tails, and because we never let our charges move faster than the speed of light, we actually cut off the unphysical tail. So actually it's a little better. It's like a model of causal diffusion. And again, then the particles go through once these little test charges pop through a hypersurface and find themselves on the other way, we can translate those into, again, via Monte Carlo and storing the weights with other charges. And the nice thing about that is I know which two charges were correlated, so I know which two hadrons are correlated. I don't have this uncorrelated background like an experiment would have to deal with. Unfortunately, during the hadron stage, you have a lot of decays and stuff, which also contributes to to charge correlations and to charge balance functions. And the way that those interactions occur, we actually do those brute force. We have to worry about the correlations of uncorrelated charges. That you get rid of by statistically doing the like sign subtraction. So we end up with two contributions. We're going to call them type 1 and type 2. The correlations from hydro are the ones that we follow these little trajectories through. And when I say trajectories, billions and billions of them. And it depends on the diffusive constant. It also depends on, I'll talk a little bit on parameter sigma naught, which I'll talk about in a little bit. And then the other kinds are correlations that arise from the cascade code. So if you just took, a standard hydro cascade combination code and didn't do any of this stuff with the diffusion equation and just took the output where every hadron that was created from the hypersurface was uncorrelated with every other hadron, you still get correlations. In fact, you get about 40% of the final answer from all such decays and stuff. And so we do that, and that's actually the more numerically intensive part of our approach. So this model has 3 adjustable parameters. The diffusion constant, what we're going to do is we're going to pick values from the lattice, and then we're going to use half that, the lattice value, twice the lattice value, and 4 times the lattice value to see how sensitive we are to diffusion. We don't vary TH. It doesn't affect things too much, except for maybe the protons. Small changes in the hadronization temperature mainly affect the proton chemistry. But the one parameter that's quite important is that, remember, we have this first surge of production at less than a Fermi over C, and if you think of that, for instance, coming from a color flux tube that is splitting, particles are pulled apart from each other so that they can get enough energy to be created into hadrons or into whatever, and so when we start our hydro code, even if we say it's chemically equilibrated, we also need to specify how far those particles are separated in special rapidity with some kind of Gaussian spread with a parameter. And so that parameter is sigma naught. And it's one of the things we want to see how sensitive we are to that parameter. So that's the main parameters that we're going to study here are sigma naught and then alter our diffusivity. Okay, so just to throw out some names here, the susceptibility was given to us from the Budapest Wuppertal collaboration, and Claudia sent all those to me, and so that was great. And the diffusion constant, it is a function of temperature. It was only calculated, I believe, the electric one, not the whole 3x3 matrix. But the diffusion that matters is the diffusion when you're in the plasma, because that's where the particles can separate noticeably. And at that point, it should be diagonal. So we're just going to use that value and say it's basically diagonal for all. Shouldn't be actually make much difference. There are lots of perturbative and different kinds of model calculations of the diffusivity also running around. They're all over the place. Lattice people will tell you maybe they shouldn't believe the lattice one because they think it is a real-time correlation, and they would tell you that the uncertainties are really hard to state. But nonetheless, there is a calculation out there. The hydro background, Chris Plumberg, who's a co-author of mine on many of these papers, he provided all of that. So when we do that, as we mentioned before, you get the correlation, you get the source functions, and then you create particles, and then you calculate these diffusive trajectories. And this figure on the right just is to give you an idea of how some of these sources evolve or contribute to the correlations at the end of the day. And I think these were SS bar correlations. And you can see that many of these, sometimes when you make the balancing charges, they will go to opposite sides of the fireball occasionally, but usually they're, because of the collective, here I'm looking down the beam pipe, but because of the collective transverse flow, they'll be focused into the same direction. Okay. If the diffusivity was 0, they'd be focused, very closely in the same direction. The larger the diffusivity, the more they can separate and spread apart from one another.
So the two colors are 2 particles in the correlator?
Right. So each one of these little pairs is like imagine Monte Carlo's the source function times d4x in each space-time, and then you decide whether or not to make a pair. Okay. And then I follow those so you can get an idea of, visually of how much the charges separate over time. And then they bounce around and separate. And these plots go until they reach the hypersurface. Okay. And occasionally you will see like this one here. This one goes this way, and this one eventually ends up in the other direction. These steps, number of random steps that occur as you're doing this random walk. I have the little particles go at the speed of light, and then to get the right diffusion constant, you adjust the time or the probability per time of redistributing or reoriented relative to the medium. And you tend to get about a half dozen such reorientations in a RHIC collision, and about 9 or 10 in a central collision at the LHC. So the whole idea of being diffusive is pretty good. You know, if you do a random walk with 6, 7, 8, 9, 10 steps, it will look like, you know, pretty much like a Gaussian. It would be pretty good representation. And this is just again to give you the picture of the algorithm that these type 1 are the ones where I showed you just what we did before, where we translate the correlation into hadrons. And the other is this brute force where I just take uncorrelated particles and then just add that to the denominator of our correlation or a balance function, and then add the two contributions together. And there are certain sum rules, like if you have integrate overall charges, it has to be 0, or the balance function has to integrate to 1. And so you can do all these tests and make sure that you're doing all this Monte Carlo, because it is kind of a tour de force of Monte Carlo to do the calculation. Now let's see what some of the results look like and compare them to some of the data. And the two people that have done the most analysis on this so far are Gary Westphal from STAR, and Jinjin Pan, who's a graduate student now. He's a postdoc at Texas A&M. He was a graduate student from Wayne State, and he really did a beautiful job actually doing acceptance and efficiency corrections to balance functions, so that they're a little bit more. You can see the physics a little bit easier once you correct for that stuff. So here's a model versus STAR just for unidentified particles. So this is the bread and butter thing. The two green lines are the type 1 and the type 2 contributions. They sum to the blue. So what you want to do is compare the blue to the data, which is the stars. This has not been multiplied by any fudge factor or anything. And that's pretty darn amazing. The left side figures are balance functions bin by a relative pseudo rapidity, and on the right side they're bin by relative angle. So this mainly tells you sort of know what you're doing. By the way, if you look at this one where the data goes up and down a little bit, that up and down a little bit has to do with experimentally trying to understand so the detectors have sectors. And so they have, little dead spots between each sector. If you look down the beam pipe, you'll see these dozen sectors or so. And then whether or not you go in between the sector can change a little bit if you're positive or negative, because positive are bending in the magnetic field and negative the other way. So when you do the like sign subtraction, you can end up seeing the oscillations from the sector boundaries. And Gary tried to get rid of those as best he could, but it's such a huge effect. He couldn't get rid of all of it. So that's why the little data stuff is going up and down a little bit. These are balance functions bin by relative rapidity again, but indexed by specific hadron species. So I make a balance function using only protons and antiprotons, and only pions and antipions. The interior bin is always a little experimentally funky, and it also has some contributions from HBT, and a small relative momentum you also have for the PP bar. You're going to have some annihilation going on. So you try not to look too carefully down here. But all in all, this is like, wow, we know what we're doing. Maybe. Things look quite remarkable. Now let's jump over and look at the results from Alice. Again, so in this case, I'm going to compare it here. They told me I'm only allowed to look at to show values from KK and pi. But actually, if you look at Jinjin's thesis, there are some other ones around too. And so, but here what I'm doing is I'm varying this parameter sigma naught. And so this is going to affect the width and rapidity, and especially for KK and PP. So let's look along here, and from here, across, and notice that because the kaons are produced early, I can, the sourcing of the kaon balance function happens, early, so if I give it that separation a head start by setting this parameter sigma naught non-zero, the balance function will get smaller and more spread out. And the best fit to the data is somewhere around a half or one, somewhere in that region. This parameter sigma naught doesn't affect the pions very much because the pions are sourced at the end anyway, and so the initial contribution is fairly marginal. But you're quite sensitive to it with the kaons or with the protons. So the first conclusion are, if we go back here and look at this, is notice the kaon balance function. Forget about the model. Experimentally, which is the same in each panel here, they are broader for. Oops, did I miss? I thought I had a different. Never mind. Okay, they are. Oops. Okay, they are broader than they are for the pions. And that's amazing, like I said. So that really tells you that there's some truth to having created the equilibrated system with the right number of up, down, strange quarks early in the collision. And so the fact that the K and proton balance functions are wider than the pions is really strong evidence that you had something along the line of this two surge production going on qualitatively. You could, no way, you would have exactly the opposite behavior if you believed that you had a highly unequilibrated system with just gluons all the way until it hadronized. And the other thing is because the fit to sigma naught seems to have a preference for sigma naught, say on the order of 0.5, but not 0. It suggests that they must have already been created and separated by the time we started our hydro. Okay, so not only were there two surges, quantitatively it looks like they had already been created and separated a little bit. It could be from the mechanism of how they're created. At the time that you're starting, you're assuming an equilibrated system. So the whole idea of assumption of running your hydro and saying I'm equilibrated at 0.6 fermi over C, it looks pretty valid. Okay, and I don't think there's anything else really that's been measured that verifies this to this degree. Now, there is a big but though, and that is what if that separation from that first surge, let's say they were made at 1 or 2 fermis over C, but there was it was just highly diffusive, much more diffusive than the lattice calculation. Well, okay, so that's the qualifier at the moment. But what we're going to go on and do next is see how we can also simultaneously understand what the diffusivity has to be. And so what we're going to look at now is the balance function bend by relative angle. And remember, and because in relative angle, this flux tube business of the particles separating and what have you, if they're made at 1 fermi over C or 0.5, it doesn't matter because we don't have this huge velocity gradient at the beginning time. There's not a huge velocity in the transverse direction. So if they start out separated by ½ fermi over C or 0.1 fermi over C, doesn't make a difference. But that difference is huge in the longitudinal direction. And so this should be quite insensitive to whether or not you made the particles at 1.2 fermis over C or 0.2 fermis over C, because the separation, they're going to add sort of in quadrature anyway. And so if you look in relative phi, and if you can stay away from the late stage production, which you can do, then you can really narrow down the diffusivity. And you stay away from the late stage production or chemistry by looking at proton or KK, because those aren't sourced at later times. They're only sourced at early times. Another thing that you could do is to even be even more sure that you're staying away from the late stage production is you can say, I'm going to look at the balance function in delta phi, but only look at pairs separated by, say, greater than pick a number of 0.7 units of relative rapidity. In that case, I completely get rid of really any contribution of any of these type 2 contributions. And I just have the contribution from the beginning. So oops. So here's some calculations. So, and as expected, the PP bar and the K plus K minus are strongly sensitive to change in diffusion. So the black line are running the calculations with the lattice value, but I could double or quadruple it or half it. More diffusion, broader balance functions. The pion balance function, because so much of the pion is sourced later on, is only slightly affected. But the K-on balance function, the PP bar balance functions should become very good tools for narrowing down the diffusivity separate from this parameter sigma naught. And that's just saying basically, except I just want to also point out that annihilation is an issue for the PP bar, and because it does show up in the delta phi, so it is an effect from the late stage that might affect our answer. And also the phi of the K plus K minus, you do have some phi decays, which is significant. And so you want to be sure you understand those. Now, you can get away from that also. Let me just jump to the next one. If we, I'll just show the results. So let's just show the results here. So here's the balance function bin by delta phi. And these, in this case, I'm changing the lattice. I'm changing the diffusivity. And let's look at the kaons here. And you can see that you start to get worse if you get away from the lattice value. I can say this, but I can't show it. But I've seen some pre-preliminary star data, and the same conclusion comes out to be true. And with pions, you're not so sensitive. But this does look like you can't have a giant diffusivity, like say, well, what if the diffusivity was off by a factor of 5 from the lattice? It does look like it has to be pretty close. And just blowing that up for the kaons, you can just see here that the having something around the lattice diffusivity does look, for the moment, better. Although the experimental data from Alice was using just a subset of their data, so that the uncertainties are pretty big still. Another thing that you can do to focus on the diffusivity is, say you want to get away from phi decays, is you only look at the width. So this is a measure of the width of the balance function. It's by taking the average of cosine delta phi, but only looking at this width as 4 pairs above a certain amount of delta y. And here, so just look at our, and by doing that, you get away from annihilation, you get away from resonant decays, you get away from HBT, experimental 2-track resolution. None of it matters if I look at the width of the balance function with delta y on the order of 1, close to 1 or bigger. And now, unfortunately, because the way we did our calculation, our type 2 correlations become very noisy, but they aren't going to contribute out here anyway. So let's just look at the type 1 contributions. The type 2 are just giving a lot of noise out there because there's not much phase space for them both to fit in the detector. But if we look at our type 1, which we can calculate without much noise, you can see that there's a large separation between these widths as I change the diffusivity. So this becomes, and again, I've seen some star data on this stuff, and the lattice value looks very good. And I'll just say that with their full statistics, that they can measure the heights of these widths to within 10% easy. And so that becomes a very nice way to maybe extract the diffusivity, say at the 50% level or better. I would say better than you can probably, I think we'll be able to extract the diffusivity better than we can extract the viscosity using, say, elliptic flow. So I'm just about done. So here's my one summary slide. So first of all, you can calculate the charge correlations as long as you assume that that you understand the local, or and we were assuming equilibrated, but you say you understand that basically the chemistry, and you assume that there are no long range correlations. You can calculate this in the standard model. It's tractable theoretically. And if I look at the balance functions as a function of relative rapidities by species, those systematics, independent of actually the calculation, really cry out that yes, we have made matter where we chemically equilibrated early on. And the second thing is that the diffusivity, I believe, we'll be able to extract with some more work as the data becomes more official. I'm quite convinced we'll be able to get it at the level of a few tens of %, as opposed to, but even if it's at which should be a little better than the accuracy with which we've been able to get the viscosity. There are a lot of opportunities both for experimentalists and theorists. I think that this reminds me a lot of my early days working in the HBT community on femtoscopy, in that we're looking at two particle correlations, and we could look at correlations for pi and pi k and kk and pp, and they all gave us different information, and we could bin it, and it was a 6-dimensional measurement. And after people worked on this for 20 years, we had all 6 dimensions of information exploited in our ability to infer what the evolution was of a heavy ion collision. And I think this is also a 6-dimensional measurement, plus it's been by species, and we're kind of just getting started here. And I could imagine if there were a big enough community and enough critical mass of people working on this, we could really start to test all kinds of physics and test different things going forward. So I'm very upbeat about all this. So I'll end there and thank everybody for their attention and patience.
Thank you, Scott. Thank you for your presentation. Now let's have some questions. So if you have a question, please raise your hand. I don't see any hands yet, so let me start with my questions first, and then we'll see. Okay, Giorgio beat me to this. So Giorgio, go ahead.
Thank you for the really great introduction to this. Is there a PP and PA? Is there anything interesting from comparing PP and PA to AA collisions?
I think so very much. Yeah, and believe it or not, balance functions were were first started at the ISR in the 80s, and the jet set parameters were adjusted to fit balance functions to get the right width. So if you run Haijing or something based on jet set, deep in its bowels are something called popcorn, and it's just some parameter to basically set how, when a string breaks, for instance, and a charge and an anti-charge are pulled apart, how much they're pulled apart. But in those early 80s, they could see, for instance, if there was a charge, there was a balancing charge close by in rapidity. But if you looked at a charge like a lambda, say you saw a lambda at very high rapidity near the end, the anti-lambda wasn't nearby, it was on the other end. So you could also, in addition to seeing this local charge production, you could actually see that when you made things, that the initial production of, in this case, initial production was pulled very far apart. Okay, and then the string broke up locally. So that whole kind of flux tube or string paradigm about how charge is made was in a way validated by this measurement.
But I mean, today all the rage is that you seem to have hydrodynamics and early equilibration and small viscosity.
Yeah, and so
is that paradigm still true?
Well, still, I mean, you have to make the particles somehow, and I think the whole question of how quarks are created in say a PP event, where do they appear? I mean, about 10 years ago, we had it was the rage of the day to talk about how the gluons equilibrated or isotropized, okay? But a bigger question is, how do you make the quarks and antiquarks? I think it's kind of a mystery as to, I mean, the experiments have been telling us, and I can go back to like E plus E minus to hadrons measures a source size and femtoscopy of 0.5 Fermis, which suggests that somehow hadrons are being produced on a size at a time scale less than a Fermi. So quarks are made faster than that. And so we know that they're made very fast, even before this. And this is basically saying, yes, this is really true. But how can you go from, you know, our CGC or whatever paradigm you like to a quark equilibration in 0.6 Fermis over C? I think it's been just a neglected question. And a lot of things that you can see, you can look at the balance functions in PP more carefully. I mean, there are questions about whether or not they're really made by, you know, pulling apart, or whether or not charges are made just by the disintegration of the incoming protons or something. Anyway, I think this early stage is wide open when it comes to understanding how the quarks appeared. Well, I don't know, what do you think, Giorgio?
No, I think this is really interesting, and
Yeah.
thanks for bringing our attention to this, because I wasn't aware of this, and indeed this is interesting.
Okay, other questions? Okay, so I have this question which I was about to ask. It's sort of a simple question related to understanding exactly where are the limitations of this study. You were quite often using the assumption that there are those quantities, chi's, which are basically calculated in equilibrium. Now, and when that exactly happens and when this hydrodynamic starts working, it's sort of a big question. So basically the thing is this: how do you see the deviations from equilibrium in this description? Does it mean that you need to modify just parameters, or does it mean that you need to introduce some additional entities in the description?
I love that question, because that's sort of where we're headed next. So the first thing was to say, well, let's assume we have the local correlation we're going to use the equilibrated values. But what we would like to do is a full-scale Bayesian analysis to see, not just say, well, that works. We would like to see quantitatively how much we can quantify that. And so now we need some kind of parametric way to say, well, let's relax the fact that the local correlation looks as chi-AB, the equilibrated chi-AB times T. Let's instead have some kind of, say, relaxation time. Let's start off with chi-AB wrong, and then given it a relaxation time, and then see if we can prove that those chemical relaxation times are short, you know, with a full Bayesian analysis, and see if we can prove that the chemistry at earlier times had to be close to the equilibrated value. And how exactly we want to, you know, put that into, you know, real words is maybe a little tricky, but I think that's what we want to do, because we would really want to quantify the statement that we had early equilibration. And I think, you know, qualitatively that's true, but we want to know quantitatively. And obviously other things we can do is we can look at some of these observables for non-central. So for everything I showed you was the most central collisions. The calculations are kind of numerically intensive, so it's not like we could do everything.
Right. Okay, thanks. Maybe sort of related question to this. When extracting this diffusivity, susceptibilities from lattice, there is essentially an assumption that the chemical potentials are zero. At lower energies in particular, there will be a substantial, perhaps non-zero chemical potential. Do you think that's important?
I mean, you can handle it. The problem is that then this extra, let's call it the unbalanced charge, it is also correlated amongst itself in interesting ways. I mean, that's the whole beam energy scan looking for critical fluctuations. And so once you assume there's some correlations besides just these local pieces, something and that's interesting, then it becomes tricky to figure out how to separate this, because you begin to sort of have to do both at the same time. And that's a long discussion. I believe me, I've thought about this quite a bit. And but in my scientific lifetime, I probably won't get there because it's kind of limited. So I'm going for the low-hanging fruit, and the stuff for, let's say, LHC energies or the highest RHIC energy are much easier to handle than to throw in, say, critical correlations related to critical phenomena or phase separation.
Okay. Any other questions from the audience?
I guess as a follow-up, because I didn't understand one main, as you go from PP to PA to AA, balance functions get narrower, right?
Yeah. If you look at that, only if you look at the pi, but not the KK or the PP.
Oh, KK and PP, they stay constant.
Yeah, constant, or maybe even a little wider, but yeah, they don't get narrower. So the pi, because the pi are related to driven by the late stage hadronization, and then in a big collision that happens when there's maybe a little, well, things cool more, then they become.
It's resonance decays too. Yeah, a lot of pi's are from resonance decays.
There's more transverse flow, which also focuses everything into smaller angles. But because you have the two surges and the KK and the PP have a chance to diffuse away from one another further in the heavy ion collision, they don't get narrower. So that's one of the signals, and that's one of the things that qualitatively you expected to see, and we do.
Sure. Thanks.
Okay, other questions? This last question sort of kind of suggested something interesting, actually something natural that I've seen in the plots, but realized just now. You have these two sources of correlations from the diffusion and from these resonances. And it seemed, correct me if I'm wrong, that basically both of them give you about the same contributions. They're almost mimicking each other. Is there a reason for that?
Well, the widths are different. If you look at the KK and the PP, in the pi, they're going to be the same, sort of the same. Well, I'm sorry, the pi gets dominated by the later. The widths are broader. Let me see if I can go back to the one for Alice, which has been corrected for efficiency. Let's see. Okay, here's Alice result. So the two contributions are red and green.
Oh, I see. Here they do look very different. Somehow I probably remember the different figure.
Yeah.
Maybe it was the lower panels.
Versus delta phi or something. Okay. But in
it was only for the pions primarily, right? I think.
Yeah. But even them, the widths are quite different. I mean, once you see how well with when they use their full data sets, and I've kind of seen this, you see that they can measure statistically, they can measure all these balance functions, even bin by species, to the width of the data point. So it's really promising.
That's fine, thanks. Okay, I don't see any other questions. So using this moment, I would like to thank you again for, oh, actually there is a question. Oleg Teryaev, sorry, I didn't realize there was a question.
Actually, just it's maybe naive question related to yours. Is there any sort of say fluctuation dissipation theorem here relating maybe different sources just of correlations?
I mean, there is. The only thing I can think of certainly the transport coefficients are expressed in terms of if you call that the fluctuation dissipation theorem, I would call it a Kubo relation. Yeah. But all correlations and fluctuations are related to one another. If you measure the correlation, then you integrate it and you get the fluctuation. So a charge fluctuation, and I've always been, a strong critic of people that look at just fluctuations of baryon number or anything else, because there's much more. If you have enough data, you can always look at a correlation, which is just basically, the fluctuation bend. It's much more differential measurement, and it's much more able to distinguish between different physics. And so I don't know if I'm not going to call it a fluctuation dissipation theorem, but there certainly is a correlation between, a relation between charge fluctuation and correlation.
By the way, as far as I understand, there is the extraction from experiment is coming by comparison of the calculations and the calculated curve and experimental curve. Is it, and you make some qualitative statements, say, about early chemical equilibrium. Is it possible, I don't know, partially at least, to quantify this, to say, to estimate errors of the quantities, say?
Yeah, that's where we're headed. It's a big project. Now we did this. We did this is a couple of years ago, not in any of the references I gave you. This is more like seven or 8 years ago. We did some simplified like blast wave parameterizations where we had instead of the two stages, we said, what if there's one contribution proportional to the strength of early equilibration spread out with one width, and then another contribution with a much narrower width. And then we treated those two widths as parameters, and we did a Bayesian analysis. And amongst the parameters, we also changed the chemistry and said, well, what if the initial contribution was, 10%, 20%, 100%, whatever of the equilibrated value? What if the strangeness, and we changed those two also? So we changed like 6 or 7 parameters. And that way, quantitatively, we could say, well, how equilibrated was and what are the uncertainties? And in that case, it looked like the amount of equilibration was basically perfect for the up-down chemistry, but with an uncertainty of like 20%, and the strangeness looked like it was 75% of the right value plus or minus 25% or something. And so we could quantify it, but that's within this paradigm or assumption of a blast wave model, which is not going to be so convincing as doing something realistic. With continuous production, and some particles are hadronized early because they're at the edge of the fireball. Some will take a long time. All that stuff is quantitatively pretty important. So to do what we did with our blast wave picture in a realistic model is basically that's the thesis of Karina, who's listening here today.
Okay, last call for questions. If there are no more questions, I would like to use this opportunity to thank Scott for a very nice presentation and staying here to answer all these questions. Thank you.